This lecture is a continued discussion of discriminative classifiers for text categorization. So in this lecture, we're going to introduce yet another discriminative classifier called a support vector machine, or SVM, which is a very popular classification method, and that has been also shown to be effective for text categorization. So to introduce this classifier, let's also think about the simple case of two categories. And we have two topic categories, theta 1 and theta 2 here. And we want to classify documents into these two categories. And we're going to represent, again, a document by a feature vector x here. Now, the idea of this classifier is to design also a linear separator here that you see. And it's very similar to what you have seen in logistical regression. Right? And we're going to also say that if the sign of this function value is positive, then we're going to say the object is in category 1. Otherwise, we're going to say it's in category 2. So that makes 0 value the decision boundary between the two categories. So in general, in high dimensional space, such a 0 point corresponds to a hyperplane. Now, I've shown you a simple case of two-dimensional space with just x1 and x2. Now, in this case, this corresponds to a line that you can see here. Right? So this is a line defined by just 3 parameters here, beta 0, beta 1, and beta 2. Now this line is heading in this direction, so it shows that as we increase x1, x2 will also increase. So we know that beta 1 and beta 2 have different signs. One is negative and the other is positive. Right? So let's just assume that beta 1 is negative and beta 2 is positive. Now it's interesting to examine then the data instances on the two sides of this line. So here the data instances are visualized as circles for one class and diamonds for the other class. Now one question is to take a pointer like this one and to ask the question, what's the value of this expression or this classifier for this data point? So what do you think? Basically, we're going to evaluate its value by using this function. And as we said, if this value is positive, we're going to say this is in category 1. And if it's negative, it's going to be in category 2. Intuitively, this line separates these two categories. So we expect the points on one side would be positive and the points on the other side would be negative. Now the question is, under the assumption that I just mentioned, let's examine a particular point like this one. Right? So what do you think is the sign of this expression? Well, to examine the sign, we can simply look at this expression here, and we can compare this with, let's say, a value on the line. Let's say compare this with this point. Right? They have identical x1, but then one has a higher value for x2. Now, let's look at the sign of the coefficient for x2. Well, we know this is positive. So what that means is that the f value for this point should be higher than the f value for this point on the line. That means this will be positive, right? So we know in general, for all the points on this side, the function's value would be positive. And you can also verify all the points on this side would be negative. And so this is how this kind of linear classifier or linear separator can then separate the points in the two categories. So now the natural question is, which linear separator is the best? Now I've again shown one line here that can separate the two classes. And this line, of course, is determined by the vector beta, the coefficients. Different coefficients will give us a different line. So we could imagine there are other lines that can do the same job. So gamma, for example, could give us another line that can also separate these instances. And of course, there are also lines that won't separate them, and those are bad lines. But the question is, when we have multiple lines that can separate both classes, which line is the best? In fact, you can imagine there are many different ways of choosing the line. So the logistical regression classifier that you have seen earlier actually uses some criteria to determine where this line should be. And it's a linear separator as well. And uses a conditional likelihood on the training data to determine which line is the best. But in SVM, we're going to look at another criteria for determining which line is the best. And this time, the criteria is more tied to the classification error, as you will see. So the basic idea is to choose the separator to maximize the margin. So what is the margin? Well, I chose, so I've shown some dotted lines here to indicate the boundaries of those data points in each class. And the margin is simply the distance between the line, the separator, and the closest points from each class. So you can see the margin on this side is as I've shown here. And you can also define the margin on the other side. And in order for the separator to maximize the margin, it has to be kind of in the middle of the two boundaries. And you don't want this separator to be very close to one side. And that intuitively makes a lot of sense. So this is the basic idea of SVM. We're going to choose a linear separator to maximize the margin. Now, on this slide, I've also changed the notation so that I'm not going to use beta to denote the parameters, but instead I'm going to use W, although W was used to denote the words before, so don't be confused here. W here is actually a set of weights. And so I'm also using lowercase b to denote the beta 0, the bias constant. And the data instance is still represented as x. And I also use the vector form of multiplication here. So we see transpose of W vector multiplied by the feature vector. So B is a bias constant, and W is a set of weights. With one weight for each feature, we have m features, and so we have m weights, and they're represented as a vector. And similarly, the data instance here, the text object, is represented by also a feature vector of the same number of elements. Xi is a feature value, and for example, word count. Right? And you can verify when we multiply these two vectors together, take the dot product, we get the same form of the linear separator as you have seen before. It's just a different way of representing this. Now I use this way so that it's more consistent with what notations people usually use when they talk about SVM. This way you can better connect the slides with some other readings you might do. Okay, so when we maximize the margins of a separator, it just means the boundary or the separator is only determined by a few data points. And these are the data points that we call support vectors. So here I illustrated the two support vectors for one class and two for the other class. Right? And these supporters define the margin, basically. And you can imagine once we know which are support vectors, then this center separator line will be determined by them. So the other data points actually don't really matter that much. And you can see if you change other data points, it won't really affect the margin, so the separator will stay the same. It's mainly affected by the support vector machines. Sorry, it's mainly affected by the support vectors, and that's why this is called a support vector machine. Okay, so now the next question is, of course, how can we set it up to optimize the line? How can we actually find the line or the separator? Now this is equivalent to finding values for W and B, because they would determine where exactly this separator is. So in the simplest case, the linear SVM is just a simple optimization problem. So again, let's recall that our classifier is such a linear separator where we have weights for all the features, and the main goal is to learn these weights, W and B. And the classifier will say X is in category theta 1 if it's positive, otherwise it's going to say it's in the other category, right? So this is our assumption, our setup. So in the linear SVM, we are going to then seek these parameter values to optimize the margins and then the training error. The training data would be basically like in other classifiers. We have a set of training points where we know the X vector, and then we also know the corresponding label, yi. And here we define yi as two values, but these two values are not 0, 1 as you have seen before, but rather -1 and a +1, and they're corresponding to these two categories as I've shown here. Now you might wonder why we don't define them as 0 and 1, but instead of having -1 and 1. And this is purely for mathematical convenience, as you will see in a moment. So the goal of optimization first is to make sure the labeling of training data is all correct. So that just means if yi, the known label for instance xi, is 1, we would like this classified value to be large. And here we just choose a threshold of 1 here. But if you use another threshold, you can see, you can easily factor that constant into the parameter values b and w to make the right hand side just 1. Now, if on the other hand yi is -1, that means it's in a different class, then we want this classifier to give us a very small value, in fact a negative value, and we want this value to be less than or equal to -1. Now, these are the two different instances, different kinds of cases. How can we combine them together? Now, this is where it's convenient when we have chosen yi as -1 for the other category, because it turns out that we can easily combine the two into one constraint. yi multiplied by the classified value must be larger than or equal to 1. And obviously when yi is just 1, you see this is the same as the constraint on the left hand side. But when yi is -1, you also see this is equivalent to the other inequality. So this one actually captures both constraints in a unified way, and that's a convenient way of capturing these constraints. What's our second goal? Well, that's to maximize the margin, right? So we want to ensure the separator can do well on the training data. But then among all the cases where we can separate the data, we also would like to choose the separator that has the largest margin. Now, the margin can be shown to be related to the magnitude of the weights. And so W transform multiplied by W would give us basically the sum of squares of all those weights, right? So this to have a small value for this expression, it means all the wi's must be small. So we've just shown that we have a constraint for the getting the data on the training set to be classified correctly. Now we also have an objective that's tied to maximization of margin, and this is simply to to minimize W transpose multiplied by W, and we often denote this by phi of W. So now you can see this is basically an optimization problem, right? We have some variables to optimize, and these are the weights and B, and we have some constraints. These are linear constraints, and the objective function is a quadratic function of the weights. So this is a quadratic program with linear constraints, and there are standard algorithms that are available for solving this problem. And once we solve the problem, we'll obtain the weights W and B, and then this would give us a well-defined classifier. So we can then use this classifier to classify any new textual objects. Now, the previous formulation did not allow any error in the classification, but sometimes the data may not be linearly separable. That means they may not look as nice as you have seen on the previous slide, where a line can separate all of them. And what would happen if we allow some errors? Well, the principle can stay, right? So we want to minimize the training error, but try to also maximize the margin. But in this case, we have a soft margin because the data points may not be completely separable. So it turns out that we can easily modify the SVM to accommodate this. So what you see here is very similar to what you have seen before, but we have introduced the extra variables, CI, and we in fact will have one for each data instance. And this is going to model the error that we allow for each instance. But the optimization problem will be very similar, right? So specifically, you will see we have added something to the optimization problem. First, we have added some error to the constraint, so that now we allow the classifier to make some mistakes here. So this CI is the allowed error. If we set CI to 0, then we go back to the original constraint. We want every instance to be classified accurately. But if we allow this to be non-zero, then we allow some errors here. In fact, when CI is very large, the error can be very, very large. So naturally, we don't want this to happen. So we want to then also minimize this CI. So CI needs to be minimized in order to control the error. And so as a result, in the objective function, we also add more to the original one, which is only W, and by basically ensuring that we're going to not only minimize the weights, but also minimize the errors, as you see here. Here we simply take a sum over all the instances. Each one has a CI to model the error allowed for that instance. And when we combine them together, we basically want to minimize the errors on all of them. Now you see there's a parameter C here, and that's a constant to control the trade-off between minimizing the errors and maximizing the region, the margin. If C is set to 0, you can see we go back to the original objective function where we only maximize the margin, and we don't really optimize the training errors. And then CI can be set to a very large value to make the constraints easily satisfied. That's not very good, of course. So C should be set to a non-zero value, a positive value. But when C is set to a very, very large value, we'll see the objective function will be dominated mostly by the training errors. And so the optimization of margin will then play a secondary role. So if that happens, what would happen? What would happen is then we will try to do our best to minimize the training errors, but then we're not going to take care of the margin. And that affects the generalization capacity of the classifier for future data. So it's also not good. So empirically, this parameter C has to be actually set carefully. And this is just like in the case of k-nearest neighbor, where you need to optimize the number of neighbors. Here you need to optimize the C. And this is in general also achievable by doing cross-validation. Basically, you look at the empirical data to see what value C should be set to in order to optimize the performance. Now, with this modification, the problem is still a quadratic program with linear constraints, so the optimization algorithm can be actually applied to solve this different version of the program. Again, once we have obtained the weights and the bias, then we can have a classifier that's ready for classifying new objects. So that's the basic idea of SVM. So to summarize the text categorization methods, we have introduced many methods, and some are generative models, some are discriminative methods, and these tend to perform similarly when optimized. So there's still no clear winner, although each one has its pros and cons, and the performance might also vary on different data sets for different problems. And one reason is also because the feature representation is very critical, and so these methods all require effective feature representation. And to design an effective feature set, we need domain knowledge. And humans definitely play an important role here, although there are new machine learning methods like representation learning that can help with learning features. Right? And another common thing is that they might be performing similarly on the data set, but with different mistakes. And so their performance might be similar, but then the mistakes they make might be different. So that means it's useful to compare different methods for a particular problem, and then maybe combine multiple methods, because this can improve the robustness, and they won't make the same mistakes. So ensemble approaches that would combine different methods tend to be more robust and can be useful in practice. Most techniques that we introduced use supervised machine learning, and which is a very general method. So that means these methods can be actually applied to any text categorization problem. As long as we have humans to help annotate some training data set and design features, then supervised machine learning and all these classifiers can be easily applied to those problems, to solve the categorization problem, to allow us to characterize content of text concisely with categories, or to predict some properties of real-world variables that are associated with text data. The computers, of course, here are trying to optimize the combinations of the features provided by human. And as I said, there are many different ways of combining them, and they also optimize different objective functions. But in order to achieve good performance, they all require effective features and also plenty of training data. So as a general rule, and if you can improve the feature representation and then provide more training data, then you can generally do better. And so performance is often much more affected by the effectiveness of features than by the choice of specific classifiers. So feature design tends to be more important than the choice of specific classifier. So how do we design effective features? Well, unfortunately, this is very application specific, so there's no really much general thing to say here. But we can do some analysis of the categorization problem and try to understand what kind of features might help us distinguish categories. And in general, we can use a lot of domain knowledge to help us design features. Right? And another way to figure out the effective features is to do error analysis on the categorization results. You could, for example, look at which category tends to be confused with which other categories. And you can use a confusion matrix to examine the errors systematically across categories. And then you can look into specific instances to see why the mistake has been made and what features can prevent the mistake. And this can allow you to obtain insights for designing new features. So error analysis is very important in general, and that's where you can get the insights about your specific problem. And finally, we can leverage some machine learning techniques. So for example, feature selection is a technique that we haven't really talked about, but it's very important. And that has to do with trying to select the most useful features before you actually train a full classifier. And sometimes training a classifier would also help you identify which features have high values. And there are also other ways to ensure the sparsity of the model, meaning to recognize the weights. So for example, the SVM actually tries to minimize the weights on features, but you can further force some features to force to use only a small number of features. There are also techniques for dimension reduction, and that's to reduce a high dimensional feature space into a low dimensional space, typically by clustering of features in various ways. So matrix factorization has been used to do such a job, and some of the techniques are actually very similar to the topic models that we discussed. So topic models like PLSA or LDA can actually help us reduce the dimension of features. Right? Imagine the words are original feature representation, but the representation can be mapped to the topic space representation. Let's say we have k topics, so a document can now be represented as a vector of just k values corresponding to the topics. So we can let each topic define one dimension. So we have k-dimensional space instead of the original high-dimensional space corresponding to words. And this is often another way to learn effective features. Especially, we could also use the categories to supervise learning of such low-dimensional structures. And so the original word features can be also combined with such latent dimension features or low-dimensional space features to provide a multi-resolution representation, which is often very useful. Deep learning is a new technique that has been developed in machine learning. It's particularly useful for learning representations. So deep learning refers to deep neural network. It's another kind of classifier where you can have intermediate features embedded in the model, so that it's a highly nonlinear classifier. And some recent advance has allowed us to train such a complex network effectively, and the technique has been shown to be quite effective for speech recognition, computer vision, and recently it has been applied to text as well. It has shown some promise. And one important advantage of this approach in relationship with the feature design is that they can learn intermediate representations or compound features automatically, and this is very valuable for learning effective representation for text categorization. Although in text domain, because words are excellent representation of text content, because these are humans' invention for communication, and they are generally sufficient for representing content for many tasks. If there's a need for some new representation, people would have invented a new word. So because of this reason, the value of deep learning for text processing tends to be lower than for computer vision and speech recognition, where there aren't corresponding well-designed words as features. But deep learning is still very promising for learning effective features, especially for complicated tasks like a sentiment analysis. It has been shown to be effective because it can provide representation that goes beyond bag of words. Now, regarding the training examples, it's generally hard to get a lot of training examples because it involves human labor. But there are also some ways to help with this. So one is to assume some low quality training examples can also be used. So those can be called pseudo training examples. For example, if you take reviews from the internet, they might have overall ratings. So to train a sentiment categorizer, meaning we want to distinguish positive from negative opinions and categorize reviews into these two categories, then we could assume 5-star reviews are all positive training examples, 1 star are negative. But of course, sometimes in 5-star reviews, we also mention negative opinions. So the training example is not all of that high quality, but they can still be useful. Another idea is to exploit the unlabeled data, and there are techniques called semi-supervised machine learning techniques that can allow you to combine labeled data with unlabeled data. So in our case, actually, it's easy to see the mixture model can be used for both text clustering and categorization. So you can imagine if you have a lot of unlabeled text data for categorization, then you can actually do clustering on these text data to learn categories, and then try to somehow align these categories with the categories defined by the training data, where we already know which documents are in which category. So you can, in fact, use the EM algorithm to actually combine both. That would allow you essentially to also pick up useful words in the unlabeled data. You can think of this in another way. Basically, we can use, let's say, a naive-based classifier to classify all the unlabeled text documents. And then we're going to assume the high confidence classification results are actually reliable. Then you suddenly have more training data because from the unlabeled data, we now know some are labeled as category 1, some are labeled as category 2. Although the labeling is not completely reliable, but then they can still be useful. So let's assume they are actually training labeled examples, and then we can combine them with the true training examples to improve categorization method. And so this idea is very powerful. And when the unlabeled data and the training data are very different, and we might need to use other advanced machine learning techniques called domain adaptation or transfer learning. This is when we can borrow some training examples from a related problem that may be different, or from a categorization task that involves data that follow very different distributions from what we are working on. But basically, when the two domains are very different, then we need to be careful not to overfit the training domain. But yet, we can still want to use some signals from the related training data. So, for example, training categorization on news might not give you an immediately effective classifier for classifying topics in tweets, but you can still learn something from news to help categorizing tweets. So there are machine learning techniques that can help you do that effectively. Here's a suggested reading, and where you can find more details about some of the methods that we have covered.